So recall from an earlier chapter or video that we looked at improper integrals of many forms, but in particular this form, and we noted that depending on what p is, this integral will either converge or diverge. So if p is bigger than 1, it converges, and if p is less than or equal to 1, it diverges. So this is going to be helpful to us when we're analyzing infinite series, because each improper integral of this form has an analog in the form of an infinite series, and they all look like this. And conveniently, the behavior of both of them are identical. So what I mean by that is, we know that, and we'll justify this, but we know this diverges. We can show that like directly, because we can take the antiderivative and then evaluate this this improper integral, and actually we'll get infinity. It's not so easy to do when you're adding up discrete sums like this, but that diverges, and that's going to imply that this guy, 1 over n to the 1, which again it's like its discrete analog, also diverges. So we're going to see that we can use the integral the integral analog of these infinite series. We can use those to figure out what the series are doing themselves. So that is the basis of the p-series test here. One way to see this visually, just while we have the pictures up here, I mean, if you think about what this is right here, plugging numbers in, that's 1 plus a half, it's 1 plus a half, plus a third, plus a fourth, right? We can represent those as areas of rectangles. So if I go up to this middle graph here, the graph of f of x equals 1 over x, notice that I can represent the area of the first. I can represent this 1 as the area of this rectangle here, the rectangle that has a height of 1 and clearly a width of 1. So that has area 1. I can represent this here, which has area, which is the number 1/2. I can represent that as, so notice when I plug in 2 into the function up here, I get 1/2. So if I make a rectangle starting here, I know that has, let me zoom in on this. There's no need for me not to zoom in. That is area 1/2. Likewise, I can make this rectangle, which has area 1/3. You can see that if I were to add up the areas of all these rectangles going on forever, well then, whatever that area is, it's going to be more than the area underneath this blue curve on the interval 1 to infinity. But we've already seen that that's infinity, that diverges. So clearly the area of all the rectangles added up must too. And similarly for these other p-series. And so that is the basis of this conclusion here. Anything of this form, you'll notice, just behaves like its continuous integral analog. So that's going to be useful when we're analyzing infinite series for convergence and divergence. So there's a useful connection between infinite series and integrals, improper integrals, and that connection is made through the integral test. So the integral test basically says that an infinite series, if it has an analog improper integral, then the behaviors of those two things are the same. They either both converge or both diverge. And I give you a quick example in the last, when I was looking at p-series in the last picture, right, I drew those rectangles and we saw that. So that's generally the idea here. So that'll help us in particular with series like this one here, because, well, that series is not a geometric, so we don't have a formula for it or a criterion for concluding it diverges. It's not a telescoping series, so we can't use partial fractions. So we're never going to find the sum if that converges. But what we can do first is let's just compare it to its analog improper integral, which is this, which I'm going to write like this, because once we do that, we'll see. In fact, to be even more thorough, I'll take the 4 on the outside in case that's distracting you. Right? We know how to handle this integral here. Let's analyze that. So we're going to write that as 4 times the limit as, a goes to infinity, 1 to infinity. And let's write this as x to the negative 1/3 to make the antiderivative easier to take. So that equals 4 times the limit. Ooh, sorry. This is supposed to be an a. The limit as a goes to infinity. Now the antiderivative of x to the negative 1/3 is 3/2 x to the 2/3. And we're going to evaluate that from 1 to a. So we get 4 times the limit as a goes to infinity of 3/2 a to the 2/3 minus 3/2 times 1 to the 2/3. But it's obvious that this is just, well, it's obvious that this goes to infinity, right? So we don't really need to simplify this anymore. If that goes to infinity, then we know that that diverges. And the integral test allows us to conclude that the series associated with it also diverges. So that is the integral test. So that's useful. If anytime you can analyze the integral counterpart to an infinite series, whatever you end up concluding on that improper integral, you can conclude for the infinite series itself. Now, of course, this is the basis of the whole P series that I introduced on the last slide. But those can just be memorized in some sense, unless you enjoy re-deriving it every time. Those can be memorized. But in general, that's really the meat and the ultimate fruit of the integral test for our purposes. But in general, if you can solve an integral, we have techniques for that because of the fundamental theorem. We don't have any known techniques for finding that sum or analyzing that because it's discrete and there's just no easy way of doing it. So this ends up being a useful tool.